Our thermochemistry in this particular course is not particularly, uh, it's not a particularly large subject. What we do want you to have some idea about what we mean when we talk about thermochemistry and the words enthalpy and the word enthalpy. And with enthalpy comes the two words endothermic and exothermic. The idea is this. It's when we do a chemical reaction, we have been spending all of our time thinking about how many moles of A or how many moles of C or grams or whatever the case may be. We maybe even thought about percent yield or limiting reagents. But we haven't really gotten quite as sophisticated as we need when we think about a chemical reaction. When there's a chemical reaction, there is a change between products and reactants. You know, there is a transformation between these things. But what we haven't really thought about yet is that there's also an associated energy change that comes along with changing from A and B into C. So that energy change typically manifests in a temperature change, and the energy actually comes from the bonds. So, you know, we think that A and B are molecules that have bonds. And if we create a new molecule, and you know, remember, I'm just making things up here, guys. If we create a new molecule that has new bonds, then there were some bonds that were broken and some bonds that were made. Along with this changing of the bonds associated with the chemicals in the chemical reaction, there's a change in energy, and you can measure this change in energy as it relates to a change in temperature. In other words, the change in temperature is related to the change in energy. So the consideration of the change in energy of a reaction this whole consideration is what we mean by thermochemistry. Now, it's not really appropriate to sort of develop some of the theory behind this. We'll save that for general chemistry. But what we want to do is we want to at least get you familiar with a couple of concepts. The concepts of thermochemical equations and what are the possible changes in energy that can occur, and how to use these energy changes in a stoichiometric equation. So let's go ahead and take a look at that. Well, if I'm going to have a reaction, and let's just say the reaction is H2 plus O2 goes to water, my good favorite standby reaction. You don't know this, but you'll have to take my word for it. This reaction is a type of combustion reaction. One could call this the burning of hydrogen, or the Hindenburg reaction, if you know what the Hindenburg is. So if I'm doing a type of combustion reaction, then it produces heat, it produces energy. You know, if you're thinking about a gas grill, the gas grill, you can use that to cook your food. You're burning hydrocarbons and oxygen. That reaction produces energy as a byproduct. So there's two possibilities. There's a possibility like this thermochemical, or like this reaction, where energy is produced in the course of the reaction. And there's another possibility. Energy could be absorbed. When I say energy is produced or energy is absorbed, I'm talking about this idea that energy could be a reactant or energy could be a product. Which one is which, do you think? If energy is produced, is energy a reactant or is energy a product? Is it here or is it here? Which way is it? Yeah. Energy is a product here. And the word that we use, there's a vocabulary word. We say that this reaction would be exothermic. So what does exothermic mean? It means that energy is produced during the course of a reaction. That means that energy is a product. If energy is absorbed, then energy is a reactant. And the vocabulary word we use to describe this is endothermic. All right, so endothermic means energy is absorbed in the course of the reaction. Exothermic means energy is produced during the course of the reaction. And you can think about energy as being a product or a reactant. Well, where does this energy come from? The energy comes, again, from the bonds. And since we are changing the bonds in the reaction from between the products and the reactants, that means that we can think about energy not only as a reactant or a product, we can think about it as a change. In chemistry, we use the Greek letter delta to represent change. And we can say there's a change in energy. However, in chemistry, in thermodynamics, we use another term, and that term is directly related to energy. It's just not called energy. We don't use the word energy. We use the word enthalpy. And this is where I'm trying to illustrate or try to get to this point that deriving the term enthalpy is not appropriate for this course at this time. But what you would need to kind of take to heart is that enthalpy is essentially energy. I can say it is energy at this level of the course or at this level of chemistry. There's no reason you can't use the words interchangeably in your mind. I'm just going to stick with the vocabulary word enthalpy at the moment. There is a little bit more of an advanced discussion when it comes to thermodynamics and physics that kind of teases out the little bit of difference between enthalpy and internal energy. Notice I added a word there, internal. But that, again, that discussion isn't appropriate here. Suffice it to say that we call enthalpy, we use the symbol H, and so delta H would be a change in enthalpy. But I'm going to talk about enthalpy as energy. The question is asked, is enthalpy or is H not heat? No, in thermodynamic symbology, heat is Q. Heat is Q. You go talk to those thermodynamic physicists and you tell them, I don't like the symbols you use. And they'll snort and laugh and say, that's why we did it that way. All right, so I'm going to come back to that equation with water in just a second. But I want to, before I do that, I want to go back to a generic equation. If I have A plus B and it goes to C, and let's call this one an endothermic reaction, then that means that energy is a reactant. And so the thermochemical equation that represents this would have the actual value of energy absorbed. If I do the same thing with an exothermic reaction, then I would put E here, and E is the value of energy released. Right? And so this one would be for an exothermic reaction. So we're talking about thermochemical equations. This is one way to write a thermochemical equation. We can say that we can use the energy and actually state the value of energy absorbed or the energy that's released. What's one important thing to point out about these numbers is that if it's a value of energy, they'll always be positive. We're saying that the energy is either produced or the energy is absorbed, but in both cases, the quantity of energy, the value, will be positive. This can be a little bit confusing because the other way to write a thermochemical equation involves stating it as a change outside of the equation. So we can say A plus B goes to C, and then I can say the delta H equals some number. Now, so this is a change. And in this case, the change in energy it can be positive or negative. It can be either one. And this is why. So this is a sort of a analogy with this, right? This is mine. So let's ignore my atrocious artwork. Or you can laugh if you want, but it serves to set up the analogy. Can the amount of money in your bank account change? Can the amount of money in your bank account change? I think most of my students, one of the students just said no. Man, let me come over to your house and borrow some money then, since your bank account doesn't change. Let me have some out of it. Let me have some out of it. For most of us, our bank accounts can certainly change. If I go to, if I withdraw $100, let's say that I have final minus initial is how we calculate change. So this would be the final balance minus the initial balance. Let's say that I had $200. That was my initial balance. And let's say I took out money until there was $100 left. So what's the change in my bank account? Type it in chat right now. What's the change in the bank account? Yeah. Negative 100. No, you're not broke. You still got $100, right? You still have $100. You started with 200. You ended up with 100, but the change is minus 100. Let's do it the other way around. Let's say I started with $100 and I added some money until I had $200. What's the change in the bank account now? It's not 300, right? 200 minus 100 is still 100. What's the difference here? The sign of the change, it's not $100 in debt, right? I'm not sure what you mean by that. The difference between the two changes is that when I take money out, the change is negative. When I take money out, the change in the bank account is negative. It doesn't mean the bank account went negative. It doesn't mean I overdrew the bank account. It just means that I took money out of the bank. The balance went down. The difference over here is that the balance went up. This is what I'm illustrating is why a change can be both positive or negative. In both cases, it's $100 difference. In the first case, we took out $100. In the second case, we added $100. Well, let's talk about it in a little bit different, though. What I'm just illustrated was analogous to this particular type of reaction. But what would be analogous to these types of reactions? Well, it's this, right? It's saying, I went to the store and I spent $100. Or I went to the bank and I deposited $100. I went to the store and I spent $100. I went to the bank and I deposited $100. Are both of those changes positive? I went to the store and spent $100. I went to the bank and deposited $100. Are both of the changes in my bank account positive? They're not. But how come I didn't say one of them was negative $100? Do you go to your friend and say, you owe me negative $100? I want your bank account to change by $100, and I want that change to be negative. You don't say that. You don't go to your parents and say, I want a new calculator. The calculator costs negative $50. Well, it's because in language, we use words that describe the direction of change, whether we know it or not. if I tell my parents that the calculator costs $100, then they know that their bank account is going, the change in their bank account will be negative because there's going to be a cost. If you deposit $100, then we know the change in our bank account will be positive because we know that's what the word deposit means. So when it comes to thermochemical equations like this, it's always going to be positive because if I have 25 kilojoules of energy that needs to be absorbed, then what we're saying is absorbed is the word that tells us the change in energy is going to be positive, right? I'm going to add energy to my system of molecules. So I could write the thermochemical equation this way, or I could write it this way. The other way to do it is, if this is in the case that energy is absorbed, which means it's endothermic. In the case where energy is released, the word released tells us that we're losing energy from the system. We're telling the reader that the energy is a reactant. So the other way to write the thermochemical equation would be to include it here as a change, but in this case, the change is negative. So these are the two different ways to write thermochemical equations. This is A, by using it as a reactant or a product, in which case it's always positive, because the side of the reaction tells us whether or not the energy is released or absorbed. This is the second way, and it's by stating the change in energy at the end. And we do have to have a sign there because the change in energy can be either up or down depending on whether or not energy is a reactant or product. If it's exothermic and you're using method B to express the thermochemical equation, then yes, it'll always be negative. But if you're using method A to express the thermochemical equation, then it's never negative no matter what. You have to then identify whether or not energy is released or energy is absorbed, in which case then you know, based on whether it's a product or a reactant, that it's that it's exothermic or endothermic. You actually see the side of the reaction that it's on. Okay. I'm gonna actually look up that. I'm gonna go back to my water example. And I want to say, let's take a look at the two different ways to write this thermochemical equation. I can go 2 waters or 2 hydrogens plus oxygen yields 2 waters. Now, I told you that this is a combustion reaction and that energy is produced. If I use method A, will the energy value be a product or a reactant? if I use method A, will the energy value be a product or a reactant? Yeah, it'll be a product. If I use method B, what will be the sign of the energy change? Will the sign be positive or negative? Right. If energy is released, if energy is produced, then our system of molecules is losing energy. And the thing that you have to kind of absorb into your understanding is that we're talking about the energy from the perspective of the molecules. Certainly the energy has to go someplace. And if you're thinking about the energy from the perspective of where the energy goes, then it seems like if we're talking about your food on the grill, then the food on the grill seems to be absorbing energy. So that is a little confusing because with every change, something is negative, but something is positive. If we go back to the analogy of the store, you lose the money. Your change is negative 100. But the store, when you bought that dress or calculator or whatever it was, the change for the store was positive 100. So there's always two sides to the story. And in this story, we're looking at it from the perspective of the molecules. So if the molecules lose energy, this is what happens when energy is released. The molecules lose the energy. The energy is, the units I've switched up to kilojoules per mole to be consistent with what you'll see. It was implied before, but really what we're saying is that this is the stoichiometric relationship of the value of energy with a balanced chemical equation. So when we say it this way, we say it is 572 kilojoules of energy released per mole based on the stoichiometry. So what that means is if 2 moles of hydrogen get produced or get consumed, then there are 572 kilojoules. And you don't usually write this, but I'm going to write it here just to remind everybody. It's released. It also means that for every 1 mole of O2 consumed, 572 kilojoules are released. It also means for every 2 moles of water produced, 572 kilojoules are, and remember, we don't normally write this part, but I just want to do it for clarity, are released. So the reason why I added the per mole was to then associate it with the stoichiometry in the reaction. And we're going to use it. We're going to use it in a chemical equation, right? I'm going to do it this way. I'm going to say, if Dr. Romero reacts 6.3 moles of H2 with excess O2, how much energy is released. And so we'll approach this problem solving the same way we have in the past. 1, what are we given? We're given that 16.3 mole of H2 are reacted. We're using these equations. Remember, this is method A and this is method B, but it's really the same equation. What are we asked for? We're asked for the energy released. So that means we're gonna calculate kilojoules. So what's the basic plan? It's to go from moles of H2 to kilojoules. And we do have a direct relationship. I wrote down the relationships that you can write from a balanced thermochemical equation. You can use the energy values, whether or not you express it as a reactant or product, or whether or not you express it as a change in energy. You can use these values to create additional relationships. And the direct relationship is between, again, it's always moles in the terms of the reaction, and whatever units of energy are given. And so we can say 6.3 mole of H2. And we know that for every 2 mole of H2, 572 kilojoules are released. And remember, we don't usually write the word release down because it's understood. It's understood based on the fact that either the value is a product or the change in enthalpy is negative. That's why we know it's released. And so when I do this, get out my calculator and do this math, 6.3 divided by 2 times 572, I get 1,800 kilojoules. Notice that this is the answer to the question. Right. We don't use negative or positive signs in the relationship because we know whether or not it's released or absorbed based on the actual thermochemistry, whether or not it's a product or reactant, or whether or not the sign is given as negative or positive. Remember, we're changing we're using different methods to express it. When we write a problem, we're using the story method. And so remember, in the story of going to the store, we say the words that mean positive and negative. We say deposit, cost. We say absorbed or released in terms of energies. When we use the symbols, the symbol representation, we have to either use these two methods, A or B, in order to tell the reader which way is it released or absorbed. So notice the question says, how much energy is released? I know you can't see the R anymore. Let's see if I can add it back in. How much energy is released? Well, it's 1,800 kilojoules. If I answer the question, how much energy is released, it's not negative 1,800. That's like saying to your mom, the calculator costs negative $50. No, the word cost already tells your mom that the money in the bank account is going to go down. The word released already tells the reader that the energy went down. Okay, and so this is what you're going to use to complete that assignment. You're going to create the thermochemical equation based on the information that it gives you, and you're going to calculate energy released or absorbed. Now, you can do this same thing. I'm going to make it just a little bit larger so we can still see it. I just can't seem to get this thing to work right. Ah, there it is. I could ask this question. If we react 3.9 times 10 to the negative 2 grams of oxygen in excess hydrogen. How much energy is released? Yeah, look at me not spelling words correct over here. Well, the same thing is going to happen here. A, what's my plan? 1. What am I given? 3.9 times 10 to the negative 2 grams of oxygen. What am I asked for? I'm still asked for the energy. So what's the plan? The plan is to go from grams of oxygen to kilojoules. But remember, just like before, chemical reactions do not speak in terms of grams. They speak in terms of moles. So I have to convert grams of oxygen to mole of oxygen, and mole of oxygen then can be converted to kilojoules. So putting it together, I would say 3.9 times 10 to the negative 2 grams of oxygen. 32.00 grams of oxygen is 1 mole of oxygen. Now we use the stoichiometry from the thermochemical equation, and it was 1 mole. I know you can't see it any, well, it is actually still right here. 1 mole of oxygen was 572 kilojoules released. And so unit analysis, grams cancels with grams, moles with moles. We're left with kilojoules. That's what we want. So the rest is just the math department here. 3.9 times 10 to the negative 2 divided by 32 times 572, and we get 0.70 kilojoules. Okay. So let me just pause real quick right there and see if there's any questions. Well, actually, before I pause, let me just remind you that we went from grams of O2 to mole of O2 to kilojoules. But I could say 928 kilojoules of energy are released. How much O2 was consumed? Remember, I can ask you a question forward, and I can ask you the question backwards. So in this case, you would go from kilojoules to moles of O2 to grams of O2. You're just doing the thing backwards. But there's all sorts of different ways to ask the question, just like with any other stoichiometry problem. All right, so let me pause right there and see if there's any questions. Yeah, so when the energy is given to you, it will be given to you with the units kilojoules per mole. And so that's what gets confusing about that is that it's what the kilojoules per mole does is it helps you establish a relationship between the balanced chemical equation, the stoichiometry, and the balanced chemical equation and the amount of energy. When we express the answer, it's just a value of energy in kilojoules. Any other questions on that? In this particular case, the value 572 would be like a constant. So Angela's already, she says, I got the answer, 551.9. I'll take it. Everybody has to take your word for it at this point, Angela. It is sort of like a constant. So the enthalpy change is a constant with respect to a particular balanced chemical equation. So this is just a little bit beyond this course. But if the delta H of this one was negative 572 kilojoules per mole, I can write another equation like this. The delta H of this one is not 572 kilojoules per mole released. Notice that all of the stoichiometry is divided by 2. So this one is 286 kilojoules per mole. So it is a constant with respect to the particular reaction that we're talking about. All right. Okay, well, let's move on from there and let's talk about electromagnetic radiation. Let's get into chapter 9. Chapter 9 starts the discussion of quantum mechanics. We're ultimately trying to get to quantum mechanics so that we can discuss how electrons behave in atoms. We need to sort of build up to that. And the first thing that we want to do to build up with that is to talk about light. Light is electromagnetic radiation. What students might not know at this very moment is that light is a very broad term. It's very broad. Certainly, light means everything that you can see, right? The light in your room, the light from the sun, the colors of the rainbow, but it means more than that. It means any type of electromagnetic radiation. And while certainly visible light is electromagnetic radiation, so is radio waves and microwaves and X-rays and gamma rays. All of those things are also electromagnetic radiation. So they're all technically light. But before we talk about light, let's talk about waves. Let's talk about waves. So here's an axis of propagation. So let's talk about the properties of a wave. What are the properties of this wave? What's this called? This would be the same as this, right? A peak to peak or a trough to trough distance. What's that? We use a little Greek letter. Yep, we use a little Greek letter. And that little Greek letter is lambda, and lambda is the wavelength. Okay. What else is there? There's something that is true for waves, but isn't really necessarily important for our class, but it's amplitude. It has to do with how high the wave is. This is amplitude, but we don't, it's not important for chemistry. It will be important for physics. The other important part about waves would be this, and it's very hard to illustrate this particular point without an animation, because it really does involve the movement of this wave. So this wave is static because it's a static picture. So it's really hard to illustrate. And so the way that I illustrate it is by drawing a checkered flag, which normally means the finish line in a race. If I count the number of waves that pass per second, if I count the number of waves that pass per second at that point, what is that? What is that called? I want to know how frequent the wave passes. And it's not the speed, it's the frequency. And so this is why it's definitely hard to illustrate it, because I need to make this wave move so that I can make it past this point and then count the number of waves that pass. It's the frequency. And we use the frequency, the symbol is the Greek letter nu. The Greek letter nu. What is the symbol for nu? It's, well, I said it's how many that pass per second. So the units for frequency are 1/second, or we also use the phrase hertz. A hertz is the unit of 1/second. Well, what's the wavelength given in? What's that? What unit is that? Meters is not common. It's not a common way to express it, but it is a length. It is a length. The common length is the nanometer. And the reason it's a common length for light is the nanometer is because that's the wavelength that's close to 1, so that we don't have to keep writing really small numbers. All right, so the units of light that we have to think about are wavelength and frequency. And there's a relationship between them. Nu equals C over lambda. And so we know what these relationships or what these symbols mean. This is wavelength. This is frequency. Does anybody know what C is? Speed of light. All right. The speed of light is a constant. Yep, it's definitely constant. And it's the speed of light. Light travels in a vacuum at the same speed, no matter what the frequency or the wavelength is. It's just that there's a relationship between frequency and wavelength such that it satisfies this equation. So what does this mean, though? Let's take a look at the frequency and wavelength. One of the consequences of light traveling at a constant speed is that the frequency and wavelength are inversely related in the same way every time. So as frequency goes up, wavelength goes down. As wavelength goes up, frequency goes down. So these two quantities are inversely proportional. Now I'm going to introduce an equation. It's an equation for the energy of a photon. But in order to do that, I need to define a photon. A photon is a single particle of light. What is usually not apparent to students is that, well, hold on a second. You just said that light was a wave. Now you're saying that light comes in particles called photons. That seems to be somewhat contradictory. And ultimately, this is at the heart of our discussion in quantum mechanics. There is a duality between the nature of light. The duality is between light's apparent ability to be both a wave and a particle. So we'll talk about that a little bit more in a second, but I want to at least define this idea. If we're talking about light as a particle, then the way that we refer to that particle is by calling it a photon. And a photon is a single particle of light. You can talk about the energy of a photon with this equation. We already know that this is a wavelength. We already know that this is the speed of light. This is also a constant. It's called Planck's constant. And you don't need to know the value. And the reason you don't need to know the value is you're not going to use this equation to do any calculations. But you do need to know the equation because I'm going to ask you some questions about how the energy and the wavelength are related. I'm also going to ask you some questions about how the energy and the frequency are related. And if we come back over here, what do we see? We see that the frequency is c over lambda. And look, there's c over lambda in the equation. So not only does E equal hc over lambda, E also equals h nu. And so this shouldn't be too far of a leap in terms of algebra. If nu equals c over lambda and E equals h c over lambda, then E must also equal h nu. And so again, this talks about the relationship between wavelength and frequency. Wavelength and frequency are inversely proportional. Well, that makes energy and frequency directly proportional, and that makes energy and wavelength inversely proportional. And the reason why I want you to be able to talk about the relationship between energy and frequency and wavelength and vice versa is because you need to understand the electromagnetic spectrum. And so what I'm going to do is I'm going to draw a type of graph. And the graph is going to be of the electromagnetic spectrum. And I hope that what you're seeing is what's happening here. What's happening at the end? What's happening to the wavelength? Is the wavelength going up or down? Yeah, the wavelength is getting smaller. The wavelength is getting smaller. So if I were to draw an arrow, I would say that the wavelength is increasing this direction. Well, what's happening to the frequency? What's happening to the frequency? Is the frequency going up or is the frequency going down? Remember that the speed of light is constant. Yeah, right. And the other thing to think about is that frequency and wavelength are inversely proportional. So if the wavelength is getting smaller, the frequency must be going up. And the last thing then to do is to say, well, what's happening to the energy? What's happening to the energy? Remember, E equals hc over lambda, or E equals h nu. Which direction is the energy going? Is it going up or is it going down? Energy and frequency are directly related. So if frequency goes up, then energy goes up. Energy and wavelength are inversely related. So if energy goes up, then wavelength goes down, and if wavelength goes down, energy goes up. So energy and frequency go the same way. There's a reason why I'm drawing it this way, because if you can draw this, then you can answer almost all of the questions about the electromagnetic spectrum. And we'll do some of those practice problems when we come back next week, but we're going to end it up here with finishing up this picture of the electromagnetic spectrum. Now, there's different types of light. You don't have to know the values of the wavelengths. You have to know their relative positions as they relate to each other. The lowest energy electromagnetic radiation is radio waves. The lowest energy electromagnetic radiation is radio waves. Right? When you turn off the radio in your car, do the radio waves go away? No. Just your car's ability to produce sound with them goes away. So you're still being bombarded with radio waves all the time, and if they were particularly high energy, you'd be in bad shape. The next one is microwaves. The next one is microwaves. So microwaves are powerful enough to heat your food, but that's about it. And only if you're in a box bombarded by them on all sides. Then we get infrared. Infrared. What comes here is visible light. And what I want to do is I want to draw a picture of this visible light so that you'll remember what colors are which. Well, let me do this next piece. The next highest energy is ultraviolet. Ultraviolet. So if I want to do the colors of the rainbow, which way does it go? Red, orange, yellow, choose it please, green, blue. Oh, this one's going to be hard, right? Indigo, and violet. Thank you. What's the mnemonic for this? You guys remember? Who is this? This is Roy G. Biv. Maddie, that's the wrong direction. It's the wrong direction. So I want you to memorize it in the Roy G. Biv direction. And the reason I want you to memorize it in the Roy G. Biv direction is that I want you to know it in terms of how it relates to frequency, wavelength, and energy. When we draw the electromagnetic spectrum in this way, we're drawing it in the way that goes with increasing energy. And so I'm doing it this way just so that you have a consistent way of understanding all of the different relationships. Okay, so we have UV. That's strong enough to burn your skin if you stand out in the sun too long. Then we have X-rays. They're strong enough to go through your skin, right? Yep. It's strong enough to go through your skin, but not your bones. And then we have gamma rays, and they're the strongest. They're the highest energy electromagnetic radiation. And they're strong enough to turn you into a mutant superhero. Just ask the Incredible Hulk or Spider-Man. Not really. Not in real life. Not IRL. Now, it's important to know that these are not to scale. These are not to scale. In fact, if I were to put it into scale, visible light would only be a tiny sliver. This would be visible light. The vast majority of radio waves that you interact with, you cannot see. your eyes are not attuned to them. Okay, I'm going to leave it there for the day.